Right, now we're going to start with vectors in 2 dimensions. This is the last topic. It is quite a big topic. Okay, so before we really start, let's do some recap on distance between 2 points. This is our textbook, page 153. Okay, so please pay close attention. Very big topic. To find distance between 2 points, you might remember that there is such a formula. Do you all actually memorize the formula? No? Is there some other way to do it? Right? No, right or wrong will give us gradient. But this formula over here that I just highlighted actually came from Pythagoras theorem. Okay? So I would prefer if you guys have less things to memorize. Even better, right? If you can memorize as little things as possible, that makes your life easier. But the trade-off is I need you to understand how this formula came about. Because if you can understand, then you're just memorizing one thing, Pythagoras theorem, and then you apply it over here. It strengthens your understanding. And every time you have to find length of a line, you are going to practice your Pythagoras theorem. Okay, so let's take a look at this example. We've got a line on a piece of graph paper. It's a line segment. It's got 2 endpoints. We've got point A, -3, 2. So the x coordinate is -3. The y coordinate is 2. Okay, very obvious. We've got our point B, x coordinate to be 1 and y coordinate to be 3. So to find the distance of this line, you see we have now created a right angle triangle. And we know that the distance of the hypotenuse is given by the square root of the sum of the squares of the other 2 sides. Meaning, if I call this A, I call this B, I call this C, A square plus B square equals to C square. Okay, this one we know. Definitely, I'm sure you guys know Pythagoras theorem, how to apply it. As long as nobody tell me Pythagoras theorem says these are A plus B equal to C, then really something wrong, huh? Shouldn't be. So A square plus B square is C square. Now, next thing, what is the distance of A? The distance of A is from here to here. This is the distance. Now, to find this distance, we can count very easily, right? 1 unit, 2 unit, 3 unit, 4 units. 4 units. How do we get 4 if I want you to calculate? Okay, so to find distance, you just take bigger number minus smaller number. Okay. Instead of just counting, just take the big number minus the small number. What are the 2 numbers? -3 and 1. What is the big number? 1. What is the small number? The small number is -3. Take calculator, press 1 minus -3. Press now. Press now and convince yourself. Big number minus small number. I do not need to memorize things like, well, if it is a negative number, I must take this minus that. No, just need to remember big minus small. Can already. Big number minus small. You get 4, right? So you don't necessarily have to count. So here we have 4 units. How did we get that? We got it from 1 minus -3. And we square it. That is our A squared. What about our B over here? The vertical height of the triangle. Obviously, it is 1 unit, right? But if I ask you to use formula, big number minus small number, we take 3 minus 2. 3 minus 2. So plus our 3 minus 2 square. This must be equal to C squared. And then C must be equal to the square root of this entire thing. B. Why cannot paste? Okay, never mind. So do your calculation, we get 4 squared, which is 16 plus 1. So C will be equal to square root of 17. Of course, you can find out the 5SF and then round off to 3SF. And the units will be units. Okay, you look at the structure of our working versus the formula over there. Don't they look really similar? And then I tell you the danger of memorizing this. The danger of memorizing this is, what if you didn't really memorize it properly? Then you're wondering, Then does the y come first or the x come first? Must it be x2 minus x1 or can it be x1 minus x2? Then you start to stress yourself. Don't need memorize, just go back to your Pythagoras theorem. You'll be okay. All those problems will be sorted by itself. Okay? So that is how we find our length of a line segment. Next, we want to go through your sine rule. So sine rule for any triangle, including right angle triangle, you will have three sides. So small a, small b, small c. You will also have three angles. Capital A, capital B, capital C. You need to be aware of the structure. When I have capital A, opposite it will be small a. That's why you have to know. Otherwise, you cannot apply a sine rule, you cannot apply a cosine rule. Because you'll be memorizing the wrong thing. When you have B over here, opposite it will be small b. And of course, C and small c. Our sine rule tells us that the length A over sine A will be equal to the length B over sine B, will be equal to the length C over sine C. That's all that there is to it. Now, I want you to put in your textbook at the bottom. Very important. Besides this format, there is another one, another version of the sine rule. Very simple. Sine A over small a, sine B over small b, sine C over small c. Okay, you need to know when it's better to use one or the other. So just like our similar figures, I've been telling you, put your unknown in the top left-hand corner. Right, sometimes you need to find the length of the small object. You put that in the top left-hand corner. Sometimes you need to find the area of the big object. You put the big area of the big object in the top left-hand corner of the fraction. Likewise over here, if the question is asking you to find length, then you use this version. If the question is asking you to find angle, you use this version. If you don't understand what I've been saying for the past 5 minutes, you go ahead and do whatever you want. You will still get it correct, provided you know how to make either the length or the angle the subject. It is the same. I'm just teaching you how to make your life easier. And finally, cosine rule. In our triangle ABC, so we are going to use the same triangle ABC. Our A square, okay, the length square, usually this is our unknown. The length square is equal to B square plus C square, so just take the other two sides, add them up. Minus 2 times of BC, multiply them, multiply by cosine of this angle. Okay, this, good to memorize, be very familiar with it. It is actually provided in your formula list, just like your sine rule. But best is if you can memorize it. Now, please do not memorize this. It is just going to confuse you. Instead, if you ever need to apply cosine rule to find angle A, you use what is given to you. Over here, the one I circled in red, you just make A the subject yourself. Don't go and memorize. Because you are expected to be able to make cosine A the subject over here already. You are expected to be able to do it perfectly. Such that you don't need to memorize this. Okay? So if you have been memorizing this for your Sec 4 N levels, my advice to you, don't. Go and practice making something the subject. It helps in your fundamentals also. Then one last thing to memorize. Okay. So now, with all those, we now expect in our vectors that we need to apply distance formula, cosine rule, sine rule. So obviously, your trigonometry not very good, your algebra not very good, you're going to struggle with it. Which is why your fundamentals are important. Okay, so scalars, vectors. That's when you first heard of this word. Probably in your Sec 1 physics. The very first topic. Then your teacher was telling you about magnitude. Oh, scalars only have magnitude. Vectors have magnitudes and direction, right? So as you study your physics, at the same time, you try to revise your mathematics. You revise your mathematics, you revise your physics at the same time. They're all linked together. So scalars, example of scalars. Over here, mass, temperature, speed. No direction. It is just a numerical value that tells you how big or small it is. Magnitude is talking about how big or small it is. Okay, has no direction. But when it comes to vectors, direction is important. So the classic examples will be your displacement, velocity, and acceleration. And then you also learned force. That's why you have your free body diagrams looking like this. You've got a box. Oh, no, wait. Usually you have a box on a slope, right? In your physics, then they'll tell you the weight of the box. So from the CG downwards, maybe it is 10 newtons. Then it is being pulled up by a force of, so this is our weight. Maybe it's pulled up by a force of 13 newtons. And then find the resultant or whatever, things like that. Okay? So these are examples of our vectors. Do you all draw scale diagrams in physics? Okay, so you have, for example, this particular case. How many forces do you see acting on this box? 2 forces, 13 newtons and 10 newtons. Did I assume something is negligible? Did I assume something is negligible? Fiction, right? Usually there's a small f over here that usually they say is negligible. So if it is not negligible, suppose I say that this is equal to 1 Newton. So now there are 3 forces acting on it. So 3 forces acting on them, they're all in different directions. There is going to be something called a resultant force. So it's like a tug of war. To simplify things, if this doesn't appear, then it's very clear. What is the resultant force? How much? 12 newtons. What direction? 12 newtons not important. Not enough. Right? Are you sure, right? Left? Up, down? Are you sure? Up? Up is like vertically upwards, you know? What is the direction? Northeast? Exactly northeast? That will be 45 degrees? No, right? It depends on how I drew it. But you got the correct idea. The force, the resultant force is 12 newtons in this direction. Whatever the direction is. But when I draw another force over here, W equals to 10 newtons, now the resultant force becomes a little harder to calculate. Jiaxuan, focus. Don't know what's on your iPad. Okay, so in our physics, you probably use a point to represent the object. And now we're going to assume that every single force is going to act on the CG. So this point is our CGR. We've got a force over here, 13 newtons, and the scale is important, right? For example, 1 cm represents 1 Newton. So on our graph paper, you're going to have to draw this 13 cm in that direction. And then you will draw another 1 cm, 1 Newton in this direction to represent the friction. 1 cm. Now you guys already know lah. The resultant is just 12 newtons in the top right direction. So let me simplify, make things easier for you. Currently, our resultant force for those two is 12 newtons, 12 cm. Okay, we have resolved these 2 forces. Make things simpler. Now I'm missing one more force, right? The downward force. It is important for me to draw to scale, and the directions are important. So following the angle over here, then draw the other side. 10 newtons. So that will be 10 cm. This angle has to be exactly the same as this angle. Otherwise, your scale diagram will not work. Okay, now tell me the length of these 2 arrows. Which one has to be longer, the 12 or the 10? The 12, very good. Do you know how to finish the drawing to find the resultant force? Parallel, okay. Which one do you all draw parallel? The 12, is it? So, something like this, is it? Exactly 12 cm, right? Can I use a solid line to draw? Why cannot? The solid one is the actual vector, okay? The dotted one is us just shifting that 12 newtons downwards. Okay, then what do I do next? Draw what? Draw this one. Draw where? That side. So what shape am I going to form? I'll form a parallelogram. Okay. So this one will be our 12 cm. This one will be our 10 cm, right? Okay, what do I do next? Draw a line from the cross to that point, is it? No. Correct. You are correct. So the resultant force looks like this. Okay. Now, can you tell me what is the magnitude of this resultant force? Magnitude. The black color one. You measure. Yes, you measure because we are doing a scale diagram in physics. So you measure. If you measure it to be, for example, what is a reasonable distance? 13. 13. Looks like 13. Okay, let's go with 13. So for example, if this is 13 cm, what can you tell me about the magnitude of the force? 13 newtons, okay? And what about the direction? Direction also important, right? Towards this angle, whatever the reference is given in your actual physics question. Okay, so this is the idea behind it. Can you imagine me requiring you to draw this kind of scale diagram for every physics, for every vectors question? Die, right? So we want you to calculate. Okay, so I will need you to calculate. For example, in this case, our missing information is this angle. So suppose I tell you that this angle is 120 degrees. Okay. So no more 30 here. I don't know what is it. So if the green angle is 120 degrees, I can include that information over here. Then I'm going to require you to start to calculate using your sine rule, cosine rule, whatever you have learned, to find the distance of this black color line, as well as the angles that are required. Yeah, so I will need the black color distance, the magnitude, as well as, for example, this angle, for you to calculate it. Okay. Don't worry about it yet. We are going to learn how to do it. So right now we have actually covered quite a lot for vectors already. Okay, so this one is your, what you already know, vectors and scalar definition. Okay, so vector representation and notation in mathematics. Just like you saw me draw arrows, I drew arrows. The arrowhead, you can put it in the middle. Normally we put it in the middle. I think of physics, you all put it at the end, right? Middle also, Okay, then I remember wrongly. So put it in the middle. The direction matters from where to where. So when I call when I name a vector, for example over here, PQ, you see a arrow above the capital P, capital Q. The arrow always points to the right when I'm writing vectors, when I'm naming vectors. It means I start from P, I end at Q, which corresponds to this P to Q. Totally makes sense, right? Okay, and also you see this little letter here, small letter A. This is another way of writing, of describing the vector PQ. So for this arrow, this vector on the left, I will either call it vector A or I will call it vector PQ. Okay, so far? Now vector A, you notice the formatting in your textbook. Did they just write the letter A? The letter A, there's no arrow. They bold it, right? You look carefully, is it bolded? It's not a typo error, it's not they do for fun. They bold it so that you know it is a vector. What if they never bold? It's not a vector, right? Then what is it? If it's not a vector, then what is it? What's the opposite of vector? So it's a scalar lah, okay? So if it is not a vector, then it's a scalar. Or it's just a number. So it is important for your exam paper, your WA, your textbook to bold it for you so that you know it is a vector. And then what about you when you have to write it? Then how you bold it? You color? No lah. Then I have so many things for you to write. You cannot be coloring everything, right? So we have a way for you to do it. You do it this way. A, and then you draw this curly thing at the bottom. Okay, this is our representation when we do on our paper vector A. You must have it. The moment you don't have this curve at the bottom, I will take it that you're doing scalar. Then all wrong already. Final answer correct, also wrong because you're doing scalar. Okay. For convenience, I will not say this curly line at the bottom. I'll just call it a worm, okay? Like it's like a little worm. Okay. So when you submit your work, you must make sure your worms are all there. Otherwise, it is a scalar. Okay, now vector B over here is also known as vector RS. From R to S. The initial point, as the name suggests, is where it starts from. R. The terminal point, as the name suggests, is where it ends. Q. Okay, now over here, one more notation. You see these two lines? And these two vertical lines. Either you write it here, you see the vector PQ inside, right? Two vertical lines surrounding the PQ, and then PQ, another way of writing it is A. The same vertical lines, but when we write it, it will look like this: PQ or A with the worm, like this. These two are the same thing, when I write it. These two vertical lines refer to magnitude. So what I have here is called the magnitude of PQ, which is of course equal to the magnitude of vector A, because they are the same vectors. So the magnitudes must be the same. Okay. Now question: can magnitude be negative? Can magnitude be negative? So things like magnitude will be your time, scalars, which only a magnitude are your time, your mass. All these cannot be negative. Okay, so magnitude only can be positive. So let's go with a vector displacement. Okay. Usually, your physics you take right side to be positive, right? So suppose this is my starting point. This is the reference point, the origin. I walk 2 meters to the right. What is my displacement now? 2 what? 2 meters. Positive, right? Because I already defined to the right as positive, and that is the normal. In our x-axis, to the right also positive, right? Okay. Well, very consistent. Okay, now, back at the origin, back at the reference point, I move 1 meter to the left. What is my displacement now? 1 meter. 1 meter long already. This negative 1 meter. Because I'm moving in the other direction. Okay, from the reference. My displacement is negative 1. But what is my magnitude of my displacement? 1 what? 1 meter. Magnitude is positive. So magnitude is the size from the reference point to where I'm standing. The distance means either area is 1 meter. But the displacement is negative 1 meter. Okay, so that those two vertical lines over there means magnitude. Things that can be measured with a ruler or with a weighing, with a scale. Cannot say weighing scale, right? Because weighing scale measures the weight, which is a vector. Okay, now, how then do we describe vectors? To the right, to the left, very simple. We know how many units to right, how many units to left. But in vectors, most of the time, they have directions that are not in the horizontal direction. For example, over here, so you see a graph paper, okay, your Cartesian plane, x and y axis. Our red color vector over here is known as vector AB. So to describe this vector AB, we start from its initial point, which is A. We want to know how to travel to point B. Okay, so with reference from A, where is my point B? So in layman's term, if I want you to describe position of point B, you probably will tell me, Mr. Wong, just go to the right 3 units. And then after that, you go up by 4 units. Make sense? To get from A to B. Okay, instead of saying, let's go directly in this direction, this standard direction. I do not know the angle. So I don't know what you're talking about. But if you say, move to the right by 3 units, continue upwards by 4 units, I know exactly what you're talking about. I don't need the angle anymore. If I want to calculate the angle, I also can. Okay, using basic trigonometry. So our vector AB is now described. Okay, so here's where you need to pay very close attention. AB is now described by 3 units to the right, 4 units to the top. Okay, so look over here. Look at the notation, the way we write it. The vector AB, Manuel. The vector AB is described by 3 units to the right, 4 units to the top. So there are a few things you have to notice over here. This looks like, what does this look like? Looks like matrix, right? But it's not matrix, huh? It looks like a column matrix. But no, it's not a matrix. It is a way of writing our vectors. Okay, and we see 2 numbers. The first number is 3. What do you think this number on top represents based on the example given? Yes, this 3 represents number of units to the right. So if I'm going to the right, I expect a positive number. Make sense? So definition, the number on top is the number of units to the right. It's not just the number of units horizontally. What about the number at the bottom, the 4 over here? 4, no, not 4 units to the left. 4 units upwards. The number at the bottom refers to the number of units you travel upwards. So when I tell you AB is 3, 4, it means 3 units to the right, 4 units to the top. How about this? CD is -1, -3. Without looking at the diagram, how many units are we moving horizontally? -1. Right? So -1 units to the, listen again, -1 units to the right. -1 units to the right. Wow, so confusing. Hey, actually, what does that mean? 1 to the left, -1 to the right means 1 to the left. Okay, so when you see a negative sign over here, it means 1 unit to the left. That's all that is. Okay, and this one over here, -3 units upwards, which just means 3 units downwards. So to go from C to D, looking at this, it means, from point C, I travel 1 unit to the left and then 3 units downwards. Let's get the diagram. There. Point C, 1 unit to the left, 3 units downwards, you get to point D. So this is how we represent, we describe a vector from the original point. It is known as a column vector. So far, so good? Okay, now that we know a vector can be described by 2 numbers. The first number is horizontally to the right, the second number is vertically upwards. We can now calculate distance between the 2 points using Pythagoras again. So please don't go and memorize your distance formula. As long as you know a Pythagoras theorem, you know that. Let's start with our line, our vector AB. The distance, the magnitude for AB is simply 3 units, you square it, plus 4 units over there, you square it, and then you take a square root. Okay? It is very easy if you draw it out. If you didn't draw it out, it is also not too tough. Look at your column vector again. This is AB. Because this means 3 units to the right, 4 units up. Then the magnitude of this vector is simply square root of 3 squared plus 4 squared over here. Likewise over here, because we are doing Pythagoras theorem. Pythagoras theorem talks about the length of triangles. Length is a scalar. So we are talking about distance, not displacement. So although this is -1, telling me that we are going to the left, when I talk about distance, I don't care about this negative sign. Okay, I can simply write my distance of CD. So this is going to differ slightly from your textbook. I can write the distance as square root 1 square plus 3 square. Because I'm only interested in the distance. I don't care whether it's going up or down. So this will give me square root 10 units. So you compare that with this working shown in your textbook. The amazing thing is that we get the same answer, square root 10. So what is the difference between my working and their working? Their working is they are expecting you to memorize a formula. What is the formula memorize? You always take this number, you square it. You always take this number, you square it. Then you add them up and you square root. But with the understanding of how we calculate distance, don't care about that already. We are just interested in the magnitudes. Anyway, when they square it, what happened? Negative times negative is still positive, right? So if you try and memorize this, wow, you may end up having more careless mistake because students may write CD equals to square root. Oh, I remember it's this x square minus plus the y square. So they write negative 1 square plus negative 3 square. And then when they start to do their calculation, turns out it is square root 8. Then wrong already. Because memorized without understanding. So if you're able to avoid doing that through your full understanding, you will avoid all these problems. Okay, so yeah, so this is the formula that they want you to memorize, but there are some dangers for that, especially if x or y are negative numbers. Okay, so let's do some quick practice. Example number 1. Just go through it first. The column vector AB from A to B, you go to the right first, 2 units, and then 1 unit up. So you simply write AB as 2, 1. No comma. Okay, no comma involved, no fraction sign. Some people write like this. 2, 1. Do like fraction. Wrong. It has to be 2 on top, 1 at the bottom. Okay, so try it 1 now. Try it 1. Very simple. How many units to right? How many units upwards? If it is to the left, then it is negative. If it is downwards, it is still negative. Finished? Okay, so double check. Are your answers the same as mine? Okay, is there any that you want me to go through? Any? Don't have, I'll move on. Y is what? RS. From R to S. We are going to the right by 3 units. So 3. Then you go down by 1 unit. So negative 1. Okay, now we move on to equal vectors. I always find this a bit strange. Equal vectors means equal vector law. Same magnitude, same direction. Okay, so same magnitude, same direction. It is going to go like this. The 2 column vectors are going to be the same. take note that two equal vectors do not necessarily have to start from the same point. Two equal vectors do not have to start from the same point. So in this case, AB and CD look, no. Yeah, here. On the right hand side, A to B, C to D. They are parallel, they have the same magnitude, but they did not start from the same point. They didn't both start from A. Okay, but they are still called equal vectors. Okay, on the other hand, AB, which is 2, 1, versus GH. GH is -2, -1. So look at the diagram. A to B, 2 units to the right, 1 unit upwards. G to H, 2 units to the left, 1 unit downward. Same magnitude, but totally different direction. Can you see that? All the blue and the red vectors, opposite direction. So when it is the opposite direction, we call them negative of each other. Which totally makes sense again, similar to our physics. Just now I was talking about the displacement, right? To your right is only to your left, which is the opposite direction, is negative. So here in our vectors in mathematics, it is not just left or right. Our vectors can be any direction. But when you talk about opposite direction, then it will be a negative vector. Okay, so here we say that GH is equal to negative AB. Okay, I want you to continue writing this in your textbook. Likewise, AB is also equal to negative GH. Okay, does it make sense to you so far? The naming, all okay, right? Okay, so let's take a look at this note over here. Hey, wait, look, point number 1. It says negative AB is equal to BA. Negative AB is equal to BA. What does that mean? Negative AB equal to BA mean? So go back to this vector, different direction, right? Look at the vector that I just highlighted. This is my vector AB, correct? What does negative AB look like? In the opposite direction, right? Negative AB, so it will be it will be this way. This is called negative AB. You agree? AB, if that's that way, then negative AB must be the opposite. Now, going this way, from the top right to the bottom left, what was the point at the top right again? It was B, right? It is still B, It didn't change. It is still B. The point at the bottom left, A. So this vector that I just drew, I said it was negative AB, but at the same time, what is it also known as? BA. It starts from B, goes to A. Oh, so negative AB is the same as BA. When I put a negative sign in front of a vector, it just changed direction. Starting from A, ending at B, just flip it around. Start from B, end at A. Does it totally make sense? Right? We said negative vectors means the opposite direction. So opposite direction, instead of starting, ending, you switch it around. Ending, starting. So we covered equal vectors, we covered negative vectors. And then the last one, zero vector means start point, end point is the same. It is known as a zero vector, also known as a null vector. So over here, zero vector, they both the zero also. Okay, it's the only vector which has no direction. The magnitude is also 0. So over here, example number 2, the vector A is given by 7, -2. So quickly picture in your mind, what does vector A look like? How many units to the right? 7 units to the right. Okay, so 7 units to the right. -2. So what direction do we go? Now 2 units. Okay, so it looks like this. They want us to do part A. Find the, what is this? magnitude. Find the magnitude. So your mind, you already drew your right angle triangle. Pythagoras theorem tells me that it is square root 7 squared plus 2 squared. Okay, I don't need you to write the -2 because Pythagoras theorem tells me that the length is 2 units. They showed -2 because they're doing vectors. They're telling you 2 units downwards. That's why they wrote -2. But in our calculation for magnitude, we don't have to do that. So 3 has that value over here. Find -8. So -8. Okay, part B, -8. Put a negative sign in front of the vector A. And what does it look like they did over here? Instead of 7, it became -7. Instead of -2, it became +2. What does this working look like to you? Huh? Matrix, right? It looks like your scalar multiplication for your matrix. Remember, the matrix multiplication of two types are scalar and matrix multiplication. So this looks totally like our matrix scalar multiplication. It's the same. And then part C, the magnitude of the vector in the opposite direction, we know that it has to be the same answer already. 7.28. Okay, so for your homework, earlier on, I already gave you the 9 question plus this. Just try to simple, try and consolidate what you have learned. All right, so we'll stop the lesson over here, class 10.